Welcome back to Discrete Structures. I'm Mirkov, and today we'll be covering matrices. To be honest, matrices are not exactly my favorite topic. However, we're going to be visiting here just for a few moments so that we can use these later on. To begin, a matrix is a grid of numbers. The matrix is defined by the number of rows and columns that it has. We always list the number of rows and then the number of columns. Here we have a 3x2 matrix. For each grid position, we can have a number, or we can have a variable that we can denote A11, A21, and so forth. In general, depending on the number of rows and columns, we will have a grid going from A11 up to Aij. And we can perform operations on these matrices. If the two matrices have the same dimensions, we can perform a sum of matrices. Here we have a color-coded example of two 2x3 matrices that we're adding together to get a result. For each position, Aij in the final result, we are taking the same Aij from the first two matrices and adding that position together. So here we can see the two numbers in red, 1 and 0, are added to get 1. The numbers in blue, 4 and 8, are added to get 12. Matrix sum is very simple. If we have two matrices which contain only zeros and ones, these are called bit matrices. We can perform a Boolean sum by performing an OR bitwise for each matrix position. Similarly, we can perform a Boolean product by performing an AND bitwise. Moving on, occasionally it may be useful to swap the rows and columns of a matrix, so we have what's called a transpose. The transpose operation simply takes the first row and turns that into a first column of a matrix, and so forth. Finally, we get to the heart of the matter. Matrix multiplication. Matrices can be multiplied together, A times B equals C, when the size of A is m by k, the size of B is k by n. The resulting matrix, C, will be m by n. Because matrices are always listed as rows columns, this means that the number of columns in A must be equal to the number of rows in B in order to perform a matrix multiplication. In our first example, we have one row and one column we would like to multiply together. In order to do this, we pair up each number within a row to each number within a column. Because remember, the number of columns in A must equal the number of rows in B. So, since we have 3 columns in A and 3 rows in B, we can pair these up evenly. This will create the result 1 times 4 plus 2 times 5 plus 3 times 6, resulting in 32. This is how you multiply a row times a column. A row times a column will always create a single number. This will be useful later. Keep in mind, however, that A times B is not equal to B times A. In our second example, we have a column times a row. You will see that when we pair up each row in A with each column in B, instead of getting a single number, we get a 3x3 matrix. This is because of the formula we described above. M by k times a k by n will get an m by n. Formally, you can define this as Cij is equal to the sum from n equals 1 to k of ain times bnj. To show this somewhat more graphically, let's look at another example. For each row in the first matrix and each column in the second matrix, we will multiply these pairwise together and sum them to get each position in the resulting matrix. When we take the purple row times the red column and sum them, we will get 2 times 1 plus 1 times 2, creating 4 in the area marked with both purple and red in the result matrix. When we multiply the yellow times the red, we will get 1 times 1 plus 1 times 2, creating 3 in the result matrix in the position marked with yellow and red. Similarly, when we take the purple times the blue, we will get 2 times 1 plus 1 times 1, for 3 in the position marked with the purple and the blue. And finally, when we take the yellow and the blue, we'll get 1 times 1 plus 1 times 1, for 2 in the position with yellow and blue in the result. I'm hammering this in a little heavily. However, do pay attention that if you swap A and B, you will not necessarily get the same result, as we can see below. Moving on, we can create what's called an identity matrix, usually denoted with an I and then a number. And this will be a n by n matrix with all zeros except for ones along the diagonal. The identity matrix has some properties that are useful to us. If we take the transpose of the identity matrix, we'll get the same identity matrix back. And if we take some matrix A, which is an m by n matrix, and we multiply it by the identity matrix of size n, we will get A. If we take the identity matrix of size m and multiply it by A, we will also get A. You can think of this equivalently as when you multiply a number by 1. The last operation that I'm going to cover is the power matrix. If you're given a square matrix A and you want to raise it to some power r, you simply multiply it by itself that many times, just as you would a normal integer. But instead of using integer multiplication, you'll be using matrix multiplication. Let's try to do something cool before the end of this lecture, so we're going to talk about the rotation matrix. Let's say you're working in three-dimensional space, for example, a video game or a robot. And for whatever you're controlling, you have a coordinate x, y, z, which represents the position in 3D space of that object. One thing you might be interested in doing is to rotate that object around an axis, such as the z-axis. To accommodate this, we've created a rotation matrix called Q, that we've set up as seen on your screen. When we multiply Q times P, we will get a new position matrix, representing the position of the object when rotated around the z-axis by theta. You may want to take a moment and actually practice doing this matrix multiplication to see why this is the case. Now that you've proved it for yourself, you can see why this is useful. By using matrix multiplication, we've made our lives easier by allowing us to rotate something by an arbitrary amount of degrees around any axis we want. If we want to rotate around an axis other than the z-axis, for example the x-axis, we need only create a different rotation matrix. When dealing with real-life objects such as robots, or those found in games such as characters, you'll find that this type of operation is used often. So let's get to some practice problems. You'll notice that before in our example, we had x, y, z, and 1 in our position matrix. That might have been a little curious for you, but you're going to see why that's useful in these practices. So let's say we have q times p for some value q. How would we represent a rotation around the x-axis? I'll give you a hint. It's pretty similar to what we did before, but we might want to move some of those numbers around. Next, I have a matrix S, which represents a different type of transformation on P. What is this S representing? Similarly, we have a matrix T, which will do a different type of transformation on P. What type of transformation is that representing? If you perform the matrix multiplications on SP or T and P, you'll see that these numbers are affecting X, Y, and Z in different ways that might be useful. Finally, we have a matrix B, which is being multiplied by P. What type of transformations are occurring here? There is more than one. And lastly, please make up some 3x4 and 4x6 matrices and just multiply them together. Give yourself a chance to just go through the math and make sure you really understand how the multiplying rows and columns together and adding them works. You're never going to have to do this again by hand, so when you're done, go have a shot of whiskey. The main emphasis is for you to understand how and why these are working, but not really to become experts in doing algebra. That's really what the computer is for.